Hi, everybody. Let me see if I can get this thing to play. So, I never actually told John what I was going to talk about. Well, I don't think he never actually had a chance to ask, I think, because I wasn't responding to emails. As a minor suggestion for what you might want to do if you're going to retire Scala World next year, is you could replace it with just a suggestion. I thought I'd throw that out there.
Will you come if I do?
I will.
Okay.
So I just took a new job a couple of months ago over at a company named Digital Asset. We do Haskell stuff, more or less on a blockchain for settling out for things like security exchanges and what have you. If anybody's curious about that, feel free to grab me sometime. I'm sure I'll be willing to talk your ear off about it. But before I took the job, I had already planned a vacation. So I went off to the south of France with my wife, and I was sitting there, and this actually speaks well to the best experience I've had involving Scala in a few years. So I was sitting there by the pool, like sipping Aperol spritzes, trying to figure out what I'm going to do and how I'm going to either gracefully let John down about coming to his conference or come up with a talk topic. And I had nothing to do, but at work we have this Haskell-like language that we have that compiles down and runs on a blockchain. I was like, well, maybe what I should do is I should spend some time learning how to build an editor for this sort of thing. And so, Paul's here and he'll be talking about Unison, so he has his own ideas about editing that you'll hear tomorrow morning. I'm going to actually stick to text. And so, but yeah, the reason I'm here is really because John commissioned that sketch and I felt really guilty. If I was going to bow out, it wasn't going to work. So, and then the choice of venue. This is the only quote I could find anywhere about Pelham. I was I was reading through a book, and Charles described the Penrith as or at least a venue near Penrith as a set of prefab huts halfway up a mountainside where it rains 6 days and 5. And it seemed like a ringing endorsement for the choice of venue. I can definitely say that the huts are not prefab. They're far older than that. As the serial concussion that I'm getting from walking through the rooms attests. So at work we're using, we write a Visual Studio Code plugin. And so with Visual Studio Code, they have this concept of what's called a language server. This is sort of a problem that a lot of us are familiar with. Like if you go to build a programming language or work in a programming language, like the support for languages and the support for editors, you have to kind of fill every point in that grid. It's a n by m kind of problem. And what they've defined is this sort of horrible JSON RPC protocol that I can talk that lets me have the Visual Studio Code thing talk to whatever implementation that I want to provide that offers up a series of events that says, oh, you want to rename a symbol, here's what it is. You want to, you've opened a document, you've changed some of the text in it. Let me know about this stuff. And I was playing around with the problem of, if I were willing to write a language from scratch, what small changes could I make to the language to make it so that this editor experience is as robust as possible? Okay, so that's sort of the question that kind of got me spinning. Like again, this was like 3 weeks ago. So as it was 3 weeks ago, this whole thing is not finished, but it at least spins up some interesting math, and I figure I can introduce the audience to some stuff that they may not have encountered before. Unfortunately, all of this will be in Haskell, so if you're afraid of Haskell, I think we've locked the doors. So again, how can we redesign a language to allow robust editor support? And I'm willing to change the language to make this go. Okay. So the first thing I wanted to note is that no computer science talk is complete without a Dijkstra quote. And this is taken a bit out of context, referring to the fact that there's two sides of the Atlantic Ocean, and this should not, that there's difference between the orientations of computer science at both sides, and it shouldn't amaze us because the Atlantic Ocean is very big. By the way, this is in Dijkstra's handwriting. I figured with the font on the website I had to use a handwriting font somewhere. If you look at the way parsing is done, it actually splits largely across the Atlantic. In the US side, you have Knuth, who invented LR parsing, and on the European side, you have Nicolaas Wirth, who turned around and gave us recursive descent, the approach that we use in Parsec and all of our parsing combinator libraries. These two schools are good at different things. If you look at like the C# parser and those kind of things, those are built in the sort of LL school of parsing. If you look at like a traditional C++ parser, they're usually in the LR school. And if you look at these two people, I think Knuth looks like he's ready to throw down. I'm just saying, I don't think Wirth has the wherewithal. Anyway, so, you know, on one side you have the sort of dragon book, the old school software development front, and then on this side you also have an old school style of development. But at least the functional programming world has embraced this side. I mean, Spiewak has some stuff for GLR, but all right. So what I want to kind of talk about is kind of a third front, you know, launch missiles at both sides of the Atlantic, which is to play around with, like, how can I parse things in parallel rather than looking from left to right, looking for the leftmost parse or for the rightmost parse. How can I adapt my language in such a way that I can parse the whole thing chunk by chunk and then glue the results together up to the root of the tree, or so that I can produce those chunks in parallel and then produce the result. So I get parallel parsing. But also, if I drop this into some kind of finger tree or something where I've annotated like the branches of this tree with a monoid, then I can dynamically change some part of that tree and bubble up to the root. And so the goal here is to say that I can try and do in sort of polylog-ish time, I'm going to have to, that ish is an unfortunate technical wibble, support all of the things in the editor up through renaming support, you know, alpha renaming symbols with capture avoidance and what have you. Okay, and so I just kind of want to explore how we can make the small changes to the language to make those things possible. Okay, so I'm going to demonstrate that we can do some parsing in a monoid, and I'll just escape out of here, start up VI. All right, so let's say that we had a soup of parentheses, whatever it was, right? Whatever parens you have, if you cancel out the ones that sort of face into each other, you're left with parens facing outward, right? So I could make a data type that holds on to how many parens do I have facing to the left, and how many parens do I have facing to the right, after I've canceled out all the ones that faced in. And then we could say, well, if you gave me 2 runs of text that were built this way, can everybody see that, by the way? All right. Then I can say that I have a monoid, I have a thing that is associative and has a unit. The unit for it is that I have no parens at all. And that I can glue 2 of these things together by sort of saying I have some number of parens facing into each other at the middle, the B's and the C's here. And if there are fewer B's than C's, then the C's overwhelm and flop over and become A's. Otherwise, we have A's and we have the B's overwhelm and they become some extra D's. Okay? And now we can define how to parse. We can say, hey, look, I'm going to parse a paren as an opening paren. I'll parse a closing paren as a closing paren. Everything else gets parsed as nothing. And I can ask whether or not, say, some string is balanced by asking whether or not, if I fold over this thing with some monoid, if I fold map with parse, which is going to produce this thing in my B, over my string, if this is the set of 0 parens facing out. With luck, I just wrote that, and I should be able to say, is that string made out of balanced parens? Is that no? Okay? So we can see that we can parse parentheses as a simple language that we can parse into using some kind of monoid. And I'm going to leave off constructing the tree and what have you. I'll just assume that we can construct such a tree. We can refine this concept. What I've done here is I've recognized something called the bicyclic semigroup. It was named the bicyclic semigroup even though it's actually a monoid because it predates the concept of monoid. But we can do this in a much more general setting, and this you can just kind of let wash over you. But if we look at this tokens type at the bottom of the screen, we're seeing I have a sequence of closing context and a sequence of opening context and some extra tokens in the middle. And so now what I'm doing is I'm pairing parens with parens and brackets with brackets and braces with braces. Okay. So this is the concept of what's called a Dyke language. They're generators for visibly pushed down languages. And in general, your programming languages tend to, quote unquote, respect a Dyke language, which is that they have more structure than just being a Dyke language. Like the tokens mean something. But if you have parens that are mismatched in your language, you have a syntax error. And so I want to look at something that's a related problem. What about comments? So these are Haskell comments. So I have a dash dash as a single line comment. And here's a closing comment. And inside of a string, I've got an opening comment. So in a void, this is just a line comment. Nothing happens. But if I am in a comment, then that dash dash doesn't happen. And this thing, the first comment is opening and closing, and this is a string. But Haskell supports nested comments, so I can be here, and now I close one of the nestings and I start another. And so what's happening here is, this is a thing that if I'm in 0 levels of nesting is nothing. If I'm in 1 level of nesting is a string. If I'm in 2 or more, it's nothing again. Okay? So it's actually quite difficult to recognize Haskell-style nested comments using a nice monoid. I'll talk at the very, very end about a technique that can do this in general. But I'm taking the incredibly brave step of noting that nested comments are not a Dyke language, and then removing them from my language. And once I've removed multi-line comments from the language, if you change their syntax to hash, no one expects them, right? Because everyone just thinks you're in some kind of shell script or something. So that's the first change. As I'm saying, I'm trying to design the features of the language by what I can parse efficiently. So let's remove multi-line comments. All right, that's if you take nothing else away from this talk. Multi-line comments are problematic because you can really only parse them from the start of the file to the end because the lexer state you're in is really ambiguous. But if I remove them from my language, now I have the property that I can always start my lexer in a known state on every individual line. And then what I could do is I could produce that sort of balanced parenthesis set for the line. And if I had a tree made out of my lines, I could fold up to the root and answer whether or not my parens are balanced. But this is actually problematic. Like, we've all written something in like C# or Scala where we opened up an extra curly brace and then the rest of the file went to crap. And whatever you have looking at this thing to turn around and automatically build started giving you, the 500 errors that you get because it wasn't able to figure out how to resume parsing. So what I'm interested in is something that in the LR school is called an error production. It's a good place to resume parsing after stuff has gone wrong. And so, I like Haskell. So what I'm going to do is try to steal the thing that makes Haskell very nice to read, and then kind of fortify it by changing some of its rules to make it provide me rich or effective error productions. So in Haskell, I don't know how many people here don't know Haskell syntax? Okay, I'm sorry. Basically, Haskell has sort of indentation style control syntax like Python. And certain keywords, where, let, of, and do, whenever you indent after one of those keywords, like I did a couple of slides ago, the indentation of put sterling there sets sort of the scope, and everything that's indented to that level is a statement inside of this do block, and anything that's indented further just is a continuation of the previous line, and anything that outdents ends this block. So if you're not familiar with it beyond that, that's enough. Okay, and if we look at the Haskell language report, buried inside of the definition, there's this little rule right here that I hate. And this rule turns around and says this: if you have a parse error while you're parsing something that's inside of a layout block, what you should do is, the moment you get that parse error, you should sort of virtually end the block. You should just try and let it kill the block. And this makes it so that if I have something like parens around a do block, the closing paren would be a parse error, so it ends the block and then resumes with the paren. Similarly, let something in Haskell, in becomes a parse error, which then ends the block and then pairs up with the let. So if I remove that one rule from the rules of layout, what I get is when a layout block ends is completely predeterminable, even if I don't understand the grammar of my language. The concept of a parse error becomes something I don't have to worry about. But it now means that these couple of examples would have to be changed a little bit. We would have to use explicit braces. Okay? And I'm willing to pay this price because now, like in the language that we use at work or in Haskell, we have references to types that come later on in the file. And I want all that IntelliSense stuff to be working even fairly robustly, even as the current definition is garbage because I've been typing and I've got an opening paren or an opening brace and I haven't finished it. But if I outdent to the top level, if the top level definitions form a layout block, then this means that the moment I get to the next type signature, I'm immediately able to recover and resume parsing again. I can make a couple of other changes to layout along the way to make it a little bit easier to parse with a monoid. One is Haskell kind of makes an assumption that tabs are exactly 8 characters wide. If you rename a symbol in Haskell, because I can start the do block on the line with the word do, changing the name might shift over this content, which might require me to indent everything on the lines below. So to make this a little bit more robust, in Haskell we tend to use the style of hanging do, where we write the do on one line and then we move down and we indent below it. If I make that sort of mandatory, now all of a sudden variable width fonts actually work. And so if you look at like Korean, Japanese, Chinese fonts, they all tend to be about double wide anyways. And so if you want to allow for names or identifiers or things that are drawn from those symbol sets, then the assumption that a character is exactly one space wide starts to break anyways. So if we make a change to layout and say instead of layout being based on a total number of characters wide, let's just talk about the sequence of white space characters that prefixes the line, and all of a sudden these sort of Asian fonts are no longer a problem. And also, as a side effect, renaming a symbol never has to affect layout, which was a nice little consequence. And so what I'm doing here is, how many people here have heard of the concept of crash-only software? Okay, couple. So there was an article sort of way back in the day that said, if you look at the software that we write, we tend to write software with some sort of graceful exit path. But all that is as an optimization means that your failure path never gets tested. So what if you don't write in a way to gracefully shut something down? Now your failure path will get very tested because every time you shut down your application while you're working on it, you're testing what happens in the failure mode. So what I'm doing here is a sort of crash-only parser development. I don't actually have the ability to successfully construct a parse tree, and I still want to have all of my editor tooling and what have you supported by looking at this, like these sort of quotients over my grammar that my grammar respects. So I'm going to say, I don't know what my language looks like, but I do know that I want it to have layout because I like Haskell. And I do know that I want it to have balanced parens. These are not big commitments, and I'm willing to give up multi-line comments. Okay, so now that we are looking at this, all of my positions inside of my terms are relative to what they've been parsing. So like you've given me a line worth of text, and I've got an error that's within the line or something. So I start needing to be able to move things around. And so I'm going to need some kind of position that I can glue together, like you've given me a change in position and another change in position. And in Visual Studio Code, positions here are lines and columns, but like we don't do tab stops. It's just total number of characters on the line. So I could build a little monoid for gluing together these positions, but it's only a monoid. I could also just give in and write the simplest form of position, which is how many bytes are there since the beginning of a file, or the number of UTF-16 code units. Now you've seen this come out of some horrible JSON parser or something like that before. I'm sure, 256 bytes into your file, there's a problem. Go figure out where that is in your editor. That's not a good experience. But I can convert between these two things in log time. And this has a nice property. This forms a group where the other one is only a monoid. So a group gives me inverses. I can talk about negative deltas. So working in this representation will matter to me. And what I want to do is I need to talk a bit about the notion of a monoid that acts on a set. So I have my errors and what have you are, like I have an error that's at some position, some delta into my file or into what it's seen. And I need to be able to move these things around. If you give me a delta that it's going to push the error, it's going to add the delta to the delta that it contains inside the error. So this would be one way to do this. Now what I'm saying here is like if I relocate by 0, that's the identity. If I relocate by the sum of two things, that's the relocation by the two things in sequence. But now, if I go to relocate a list of elements, this is perfectly fine. I could write this instance at the bottom. But a list of elements could have n things in it. It's just going to take O(n) time. And if I kind of want to get down into that sort of polylog time as I do dynamic things, I can't spend that long pushing around my errors. Even if I have a lot of errors, I don't want to spend that long pushing them around. So what I need is a way to push around a list of errors in O(1) in order to be able to hit the kind of time bounds that I want to hit. So this is a lot of stuff on a slide. And unfortunately, I don't have a laser pointer here. So we look at the definition here. All I'm doing is I'm changing the definition of a list to put a delta into each const cell. And what I'm saying is when I relocate the list, push the delta into the const cell. Don't push it down. So this delta applies to not just the head of the list, but every element in the list below. And then whenever I go to pull something off the list, that's what this unconst operation does. If I go to unconst from the empty list, I get nothing. But if I unconst from a const cell that has a delta in it, I apply the delta to the head of the list as I give it back to you. And I apply the delta to the tail of the list, pushing it down. And so this remains O(1), and I was going to do O(1) work to inspect. So I've pushed the charge to the use site. Okay, so this is one way that I could do relative positioning on lists. Do I have a question? Oh, is that a laser pointer? Almost. So this notion of having a monoid that I can push down kind of slowly through a structure gives me a lot of tooling. And by the way, if I know a little bit more about delta than I know about a monoid. The fact that I have a group here means that what I could do instead is I could just have a pair of a delta and a list. And if I go to const onto this thing, then what I should do is, I want a constant element onto a list, but everything in this list is going to have this delta applied to it. But since I have inverses, I can apply the opposite shift to the elements I'm going to put in the list so that when I go to pull it out, it'll be exactly what I put into the list. So having a group lets me avoid having to affect every single const cell, which shrinks this structure back down. But it also turns out, like if I start playing around with some other kind of containers, like we can do, once we have lists, Chris Okazaki wrote a book on purely functional data structures. And in it, he basically addresses the problem of how do we work with asymptotic analysis of algorithms in a functional setting, okay? Because now you no longer just have one object. You can always go back in time and look at the old versions of an object. Everything's persistent. And so the classical techniques for amortizing performance don't work. And so in Okazaki's book, he turns around and says, well, here's how you use laziness to address these performance issues. And so he builds up a bunch of queues and data structures that have all sorts of nice performance guarantees. But they're all kind of like they sit on some kind of list. So if I can relocate lists, I can relocate queues. Given the ability to relocate queues, I can relocate catenable lists, all this kind of crazy stuff. So I can get lists that give me O1 append that I can relocate in O1 time, and I can give you all of my errors that are coming out of my thing with just the sort of the log up to the root cost to make changes to that set. And now let's see, I'm going to start trying to get other things out of these maps, or out of these ranges of text. An example would be like a map of positions to names, or where are the occurrences of this name in this source file, would be the kind of thing that I'd start to accumulate out for like free variables. What are all the occurrences of free variables inside of my syntax tree? But I want to be able to relocate the entire map full of errors, or full of positions, in O1 time as well. In order to be able to talk about that, if I have a map, like an ordered map, where the keys have some kind of ordering on them, what I want is that if x is less than y, then if I were to relocate both x and y by some delta, then they should have the same relative ordering. Like if x came before y before, if I shift it around, it should still come before the other. And then under those assumptions, I can build a map. Like this is like the map that we have in the containers library in Haskell, such that I just shove this delta down into the map. And then whenever I would like do an operation on the map, the delta would get pushed further down into the map past whatever I'm looking at. So if I were to do an insert, I'm going to burn like a path into my map with 0 deltas along it by shoving the deltas off the path. Now, the only problem with that is it sort of changes the performance characteristics of maps. It makes everything about 4 times more expensive, because instead of just touching the path that I'm walking down the map, I also touch the key, the value, and the other branch to shove one thing down into each one of them. So it made all of my map operations about 4 times more expensive. But I have a group before. That's one of the reasons why I switched delta around earlier. So now that I have a group, what I could do is I could leave the deltas intact along the path to wherever I was going to insert my element. And that's going to cause me to want to shift my keys and values off to one side by whatever the accumulated delta is along the path. And then I can push back by using the inverse of that delta. And so whenever I go to access that element, it'll be at the right position. And that fixes the asymptotic performance of maps. Now, if we want to draw a trick from the bag, from Phil Bagwell's bag, we can turn around and say, look, if you look at like hash array map tries, now the auxiliary paths, like if I'm looking at any individual node in a hash array map try, they're like 16 or 32 other children. And so I don't want to push the delta off the path into all 32 children, because that's going to be a much bigger factor that I would lose. So if I start doing this for hash array map tries, then having this group structure actually becomes quite important. But now if I start gluing these things together, we start running into sort of a funny problem. So like if you give me a monoid that is how much text have you seen, and you give me a monoid that describes all of the positions at which names occur as a map, I need to be able to glue these things together. And it's not like the product of the 2 monoids that I have. It's not just glue together the 2 sizes to get a larger size and glue together the maps like with the positions exactly where they are. What I actually need to do is I need to kind of shift the positions in this map over before I merge the 2 maps. And in group theory, there's this concept of something called a semi-direct product of 2 monoids or 2 groups. And this pops up all over the place in math, and it's usually never given the appropriate name. So I want to kind of like point to this and say, hey, look, this is a pattern that occurs over and over and over again. And maybe you can look for it, because it pops up if you start doing serialization or deserialization. Like I want to serialize something out to a buffer, and I can tell you how big the buffer will be, and I can serialize something else out after it. What I really want to do is I want to shift out the region that I'm serializing to the range after this thing, based on the size that this thing is going to fill. So we'll write to disjoint memory, or read from disjoint memory. And so what we're saying here is this P thing is saying, hey, look, I want to glue together the sizes, but when I go to glue together the maps, I want to relocate the one map by the size of the left-hand side. So it's shifting it past whatever it was. And this pattern pops up. I wrote an article on like computing CRCs in parallel. If I know the size of the window for which I have a CRC and the size of another window for which I have a CRC, I can glue the CRCs together. If I have a hash that's computed modulo a prime, and M and N are the number of bytes that I've recognized for each one of those, where A and B are the hashes, then what I can do is I can just say, hey, look, add 2 to the M times B to shift it past. And that will work because my prime will be hopefully co-prime with 2 to the M. So what does this look like if we actually try and turn it into code? So I can say, hey, look, there's I'll make something I'll call a relative monoid, which is a monoid acting on a monoid in such a way that, like if I were to relocate 2 things that I were gluing together, it would be the same as if I'd relocated them independently and then glued them together. Like it distributes nicely. And we can talk about this sort of semi-direct product of my change in position and some other thing, like a map from positions to values, or positions to names, or from names to positions. And it's not quite the usual direct product. And now what we can do, now that we can have this notion of, given a range of source, and I've got the positions at which all those names occur, what I want to be able to do is start talking about name capture. So far what I've done is I've started identifying little sub-languages that my programming language will respect. It will respect parentheses. It will respect layout. And layout wins so that I have strong error productions. But I still want to be able to do things like find all the occurrences of a name even in the presence of garbage, right, as a user is typing. I want the renamer to not break and be brittle while you're working on a partially completed source file. And so I can make an observation about names at a sort of source level. Whenever I'm going to say at a source level because normally when we talk about syntax, we imply that there's some kind of syntax tree. And when you have this garbage, I'm not actually able to produce a syntax tree yet. So what I want to be able to do is work purely at a textual source level and try and come up with notions of name capture, of like you've got a lambda and it's bringing this name into scope inside of this nested context that only exist at a source level, or that such that if you were to build a syntax tree, we'll get the same notion of what's captured if you're able to parse. But if you're not able to parse, it still does something sensible. And so I can make the observation that in a source code level, names are only kind of captured for a finite number of intervals. Now this is a vacuous statement because there are only a finite number of intervals over a source file. But these intervals have an interesting property. They never kind of partially overlap. You never have a binding construct that brings in a name into scope for, say, the first 50 characters, but another one brings a name into scope from the 50th, or from the 30th to the 100th character, where there's this funny interval of overlap. If I bring a name into scope and somebody else brings a name into scope inside of any language that I care about, these intervals nest like Russian dolls. You get this sort of, they're either disjoint or one is contained within the other, or they're exactly the same size. And what this has is, this provides me the nice property that I can always sort of uniquely identify the nearest containing binder by building up a little interval map. And these interval maps will never have partially overlapping intervals. And again, all of this stuff for relocation allows me to relocate entire interval maps, to slide them around as I'm working. So I kind of like this sort of notion of, let's look at name capture at a source level, and it builds this sort of weird de Bruijn index out of the containing intervals, rather than parsing into a traditional syntax tree. And once I have this is enough to be able to support the renamer, where the renaming can say, hey, look, I want to rename all occurrences of foo inside of the interval at which this binder covers. But now we have to start locking in a little bit more of the grammar. We have to start being able to say, well, what do binding sites look like? And if I pop back over to here, Like a binder here, like balanced x's. X's is in scope for the current statement, but balanced is brought into scope for basically the whole file because for this entire scope. Parse also is bound for the whole file. A and B and C and D here are bound for the statement, so they're in scope over these 3 lines. So I can work out at a very detailed level exactly the set of intervals that names are captured for. So I think this sort of gets me to a summary. So again, if we play with the rules of layout, we can have a Haskell-like language where no matter what you're doing, you can resume parsing. We don't have the standard dangling C#, C++ style, you've opened a curly brace and you're stuck. It seems to me that multi-line nested comments are the enemy. At least I don't know how to deal with them. We can support a lot of the editor functionality without ever producing a real syntax tree, which was for me kind of a bit of a revelation. And when I said earlier it was sort of polylog-ish, if I only had to map from locations to names, then I could get away with polylog time. But if I ever have to build a map from names to locations such that I glue all the positions together, then the total number of names in my file infect my asymptotic performance. And so I have yet to be able to get everything to work with the interval map without having to build that secondary map. If I could get away from that map, then I could get everything down into sort of this nice log-ish time as you edit. Now, the other question is this a good idea, right? I'm able to give you like super fast editor response and start highlighting everything in red immediately. Now, maybe you don't want that, but getting it fast enough that you have the option to say that you want immediate feedback or you want to wait a couple hundred milliseconds or a couple of seconds before you parse, at least exchanges the dialogue that we have. This notion that I'm pushing the monoid down through my tree structure works for other monoids other than just changes of position. If somebody wants to grab me later, we can talk about how you can do like name capture and substitution using a similar construction. There's also but this also works for any sort of category that acts on Haskell or acts on Scala if you really want to do it there. Somebody might. And again, this sort of notion of a semi-direct product gives me this notion of here's a description of some interval and here's a description of another interval, and let me shift them around as I go to merge everything together. And it's a very general pattern. So that's really all I've got. It was sort of a nice little whirlwind tour of a little bit of math that doesn't come up very often. Are there any questions? And do we have any time?
Could people repeat the question? We've got 5 minutes.
Okay.
If you could repeat the question, because we don't have an audience mic.
Okay, yes. If anybody has a question, I'll happily repeat it. Runar. Runard, can I show you again the notion of a semi-direct product? Yes, here we go. So a semi-direct product is, I have 2 monoids, in this case delta and something else. Here I have this notion that if I were to act with one monoid on the other, then that action distributes over mapend and it's unitary. So if I relocate unit, I get unit. And then so I can if I had a map as like A here, then I can literally relocate the entire map because we worked out earlier how to relocate maps as a monoid, or relocate maps. And maps form a monoid. I can union them together. So now I have this notion here that, what is happening is that the unit here looks like the unit for the direct product of 2 monoids, right? Normally you would just say M append N and A append B. But we've got this little flip down there where we relocate by M, B. Yes?
This looks to me like a great foundation for a date and time library that deals with sort of human-readable date deltas that actually can be relocated appropriately along the timeline such that they change in...
That's going to be a very difficult question to repeat. So Chris was noting that this sort of forms a decent basis for a time library where these are sort of based on relocatable deltas of human readable time, as I'm understanding the statement. Anybody else? Paul?
Yeah, do you have, I'd love to see just an example of like a full parser or like a full work example.
So I do have code here. I've got a pile of references here on the last slide. At GitHub Kmett Coda is the name of the project that I'm currently working on this under. I have the code base that runs this, and that has the language server protocol. I'm missing a few pieces. I more or less started working on this right before ICFP, and then I got sucked into ICFP, and then I went down to Zurich, and I haven't really stopped traveling ever since I started working on this thing. So I haven't had a whole lot of time to finish. It's all but there. But you almost, probably by the time I leave here, we can get to the point where we have a fully worked example. But if you look at the code under Coda, there is the machinery for building the finger trees and what have you that we need to work line by line through your file. I don't know if I actually repeated that question, but anyways. All right, thank you. Thank you very much.